This is the 10.1 Conics in part 2. Now, we've done the parabola and then the circle. Let's move on to the third type of conics called the ellipse. Again, we're going to define ellipse a little bit different from what you actually know, right? So an ellipse, you know, it's going to look like an oval shape, right? Like this. But there's a special properties about these oval shapes. It is more like a circle, okay? It's like a circle, but distorted in one direction. So think of it as instead of a circle having having one fixed point called the center, the ellipse actually has two fixed points, one over here and one over there. Get two fixed points. Then if you fix a total distance, okay, so what I mean is, let's say you pick a point here and you measure the distance from this fixed point and this fixed point. Let's say he's have distance 3 and distance 1. So you say the total distance from these two fixed points is 4, right? If you look at another point on the ellipse, so say here, again you measure the distance from this fixed point and from this fixed point. I'll make up the number, say here you have 3.2, and that distance here has to be 0.8. Why? Because 3.2 plus 0.8 gives us 4. Likewise, if you pick any other point, it doesn't matter where you choose, okay? So the total distance from this fixed point got to be 4. And this is 3.9, and that's going to be 0.1, so the total would be 4. Okay, so an ellipse could be described as a set of all points. Okay, sets of all points, the sum of whose distances from the fixed points called the foci is constant. Okay, let me say that again. If you take the set of all points x, y, okay, and you look at the sum of whose distances from these two fixed points is constant. Those two fixed points is called, so that one, foci. Okay, foci is a plural form of focus. Okay. All right. Now the line through the foci intersect the ellipse as 2 points. If you look at the line that through these two foci, it intersects the ellipse at this point right here, this point 1 and this point 2. These 2 points are called vertices, so I can label V1 and V2, that is vertex 1 and vertex 2. Okay, and then you have the focus 1 here, and then the focus 2. The chord joining the vertices is called the major axis. So this chord right here in the, like a circle, the inside of this ellipse called the major axis from V1 to V2. The midtone point is the center. Its midpoint is called the center of the ellipse. So if you look at the midpoints of this chord or this major axis, we have this point right, midpoint right there. That is the center. Okay. The chord perpendicular to the major axis at the center is called the minor axis of the ellipse. The minor axis. If you draw the chord through the center and perpendicular to the major axis, this is called minor axis. Okay, so now think about this. If you think of this as a circle, right? So in a circle, if you draw any chord through the center, you got what we call the diameters, right? You have the circle, and then when you have the center here, if you draw any chord through the center, they all have equal length, and we call them diameter, right? Unlike circles, since it's been distorted, if you draw any chord through the center here, it has different lengths. The longest length is this one, in this case, the horizontal one, we call the major axis. So the major axis has the longest, is the longest chord of the ellipse. The minor axis, on the other hand, is the shortest chord of an ellipse, and they are perpendicular, right? I have another diagram here for you to visualize the vertex, focus, okay, majors, minors. Now the center, we're gonna again label that HK is locations of the center. Now in this case, the major axis is horizontal. We might consider the case where the major axis is vertical. Okay, so if the major axis is vertical, you can expect to see a longer, and this time, remember the major axis is the longest chord inside of the ellipse. If this were the major, then the minor will be the one that's shorter, right? If you have like it's a center, so let's say it's a center, then the major axis is gonna be smaller for sure, right? I mean shorter. And if you look at the ellipse will go like this. Right, so make a very nice ellipse. So you can see the ellipse go like this, where the major axis is vertical, the minor axis is horizontal. Then all the foci, vertices, lines on this vertical major axis, right? Now, the equations of the ellipse, we have two forms, like similar to the parabola, right? Depends on where we have the horizontal or the vertical major axis. Right, so here's a formula. The standard form of an ellipse with the center at HK. Okay, it's the center HK. And major and minor axis of length 2A, where A is greater than B. So if we have a major axis that is horizontal, that has length 2A. So in other words, if the distance from this vertex to that vertex is 2A, that means from vertex to the center that has length A here, from here to here has length A, right? So A. And then the minor axis has length 2B, which means the distance from the center to this point here has length B, and that has length B. notice that the A got to be bigger than B, right? A longer than B. Then the formula will be x minus h squared over a squared plus y minus k squared over b squared equal 1. Again, hk is location of the center, a is its length, b is its length. If we have the vertical major axis, you see that the formula look the same with a squared and b squared swap in the denominators. And then the vertical major axis, the A is actually that distance here, and that is the A. And then here's the B, and that's the B. Okay, so you see the location got changed a little bit. You see the A here is under the X when you have horizontal major axis, and the A will be under the Y if you have the vertical major axis. Now, in this diagram here, the focus, okay, the focus is right there, okay, it's on the major axis. Now, the focus or the foci, two foci, lie on the major axis, C unit from the center. So that means the distance from the center to the focus, I call this C. Then in fact, the A, B, and C, this distance here, are related. And it's related by the formula here, C squared equal A squared minus B squared. Okay, so if you take A squared minus B squared, and you take the root, you got the length between the center and the focus. We don't have time to go over the formula. I mean, where do this formula come from? You may want to read the book or the video in the e-text and find out more. Let's look at an example. Find the center, vertices, and the foci of the ellipse given by x squared over 16 plus y squared over 9. Now notice that the it's belong to, first you have to recognize it belong to the first or the second form. And how do we know? Well, don't forget that A is bigger than B. So the difference between the two forms is the denominator A squared is a larger denominator under X, or the larger denominator under Y. So what I'm looking at is, you're looking at, the 16 and the 9. 16 is bigger than 9, so that's under X squared. So we will have this case, which is the horizontal major axis. Okay, so from here you can identify what is A squared. Well, A squared is 16. What is B squared? B squared is this number, right? So it is 9. And what is H and what is K? Now I have x squared, so x minus 0 squared. So the H and the K is understood to be 0 in this case. When you find out H and K is 0 and 0, again, that will give you the locations of the center, which is at the origin. For A squared and B squared, want to identify, you can find a solve for A and B easily. It's 4 and 3. Okay, so that's give you 4 and 3. Now, so what does it mean? What does it tell us, right? So it tells us that the vertex will be at the center. Okay, So it will be at the center. So let me draw. Yeah. Okay, so right, so I have the coordinates like this, right? Right, now move it to a little bit to the left. Okay. What I know is the center will be at the origins. So that's the first thing I know, right? So he's a center right here. Okay, at the origin. And then the A is 4, the B is 3. So don't forget what is A and B. So A is the distance from center to vertex. B is center to the other points on the ellipse, which is on the ellipse. Now, because I know a square is under this, I know this horizontal major axis. So your A will be horizontal move, right? So we're gonna move 4 units to the left, and the A is 4, so I move 1, 2, 3, and 4. So that will be a point, and this is actually the vertex. Okay, 1, 2, 3, 4. So at -4, 0, I have another vertex. So that is really your V1, and that's your V2 vertices. And then the B is 3, I move up 3, 1, 2, 3, and 1, 2, 3. And these points, we don't have the name, and these points are also on the ellipse. Okay. Now, normally, before you draw ellipse, we're going to draw the rectangular box through these 4 special points. That will help guide you draw the ellipse efficiently, right? So your ellipse is actually inside of this rectangular box, and these sides serve as a tangent line to these ellipse. Okay. So let me try. Let me see if I can use the tool here to draw it much better. Let me see. I can have. So see, I have this ellipse here. It's go through the 4 points that I just plotted, right? So that is the graph of the ellipse. And again, we are asked to find the center and the vertices. And so what the answers, right? So the center is at 0, 0. Got that one. So at the origins, where the vertices, so vertices right here, it's -4, 0, and over here is 4, 0. So we're going to have V1 -4, 0, and V2, it's 4, 0. Now, how do we find the foci, right? So that's important. So the foci, you have to figure out the C, right? C is the number of units from the center. That's where we find the locations of the foci. So in order to find out, we're going to use a formula here. It's C squared. What's C squared? Okay, so C squared is A squared minus B squared. And A squared is 16 minus B squared is 9. You got 7. That means your C is root 7. Technically, it's plus or minus. I think all of B is supposed to be plus or minus. It's root 7, but I'll keep it as a distance, so root 7. So what it means is from the center, the foci will locate root 7 units away from the center on both sides, right? So it will be, what's root 7? Root 7 is 2 less than 3, so number 1, 2, I think it's somewhere over here. And somewhere over here, it's 1, 2, so W is your focus 1, and that's your focus 2, right? I think I have a little better graph here with the ellipse, okay, vertices, the foci, and the units, I didn't write it down, right? So he is root 7 unit away, so we root 7, comma 0 for that, and negative root 7, 0 for the left focus, okay? Now, on the other hand, we might have the ellipse that's not written in the standard form, right? That one easy. It's really put it in that form. But when you have the ellipse that is not in the form, they find the center, vertices, and foci of the ellipse given by this general equation for x squared plus y squared minus 8x plus 4y minus 8 equals 0. Then our task is to rewrite this in the standard form. Same way we did it with the equation of sphere back in the beginning of the semester. So to do so, we got to complete the square. We're going to group the x terms together, the y terms together, then we complete the square. So here's the step, actually showing here. Keep out too much information, but we put 4x squared and then 8x together, so I group them. The y squared plus 4y, so I see group them, so it's over here. The negative a move to the other side to make it positive 8, since there's none of this business, none of his business there. We were looking at this and this, right? And to complete a square, I group these two together. Now, in order to complete the square, you need to have leading coefficients be 1. So you don't want the 4, so here we factor out the 4. If we factor the 4, we have x squared and then has minus 2x. That one's supposed to be blank. And then you have y squared plus 4y, that's supposed to be blank. We leave that space there and determine what do we need to add to make it a perfect square trinomial. And as we do, you take half of 2 and square, you got 1. And so we add 1s here, right? So that's why we add 1 here. And then here, take half of 4 is 2 squared, got 4, and then we add 4 over here. Now, since this is an equation, you need to add on both sides, but you know, we add the same amount on both sides. This is 4, so we add 4. This is 1. Why do we add 4? It's because we multiply the 4 and the 1, right? So it's inside the parentheses. If you multiply it out, we really add 4 on the left-hand side. We have to add 4 on the right-hand side to balance it. And after this step, it's become an x minus 1 square. It's a square of the binomial x minus 1. And that become a y plus 2 square. By these three terms, we got 16. And if you look at the formula, we have to have 1 on the right-hand side. So we decide to divide both sides by 16. Right, so that become a 1, and that's over 16. 4 over 16 we reduce to 1 over 4. There. Okay. Now, when we have the right form, okay, so that is the right form. It's matching which one, by the way? We have two forms, first and second. Again, how do we know which one? We just look at the denominator, 16 versus 4. 16 is bigger than 4. It's under the y. 16 is under the y. So it's going to be the second form here. So in this case, we have vertical major axis. With a squared is 16. Right, a squared is 16, b squared is 4. Okay, and we also notice that that's your h. So h is 1. So I have h is 1. The k will be -2. The a squared is 16. Therefore, a is 4. B squared is 4, and so b is 2. Then from here, I can figure out the c again using the same the formula. C squared equal a squared minus b squared. So the c squared is 16 minus 4. When we solve for c, we take root from both sides. We end up with c is root 12. Okay, c is root 12. Now, the center, again, is 1, -2, h, and k. And how do we locate the vertices? I have 1 and -6, and 1, 2. So the way you do is, again, you locate the center first. Will be is 1 and -2 there. And the A is 4. Notice that we have the second case, the vertical major axis. So from the center, you're going to move up and move down 4 units to locate the vertex. So if we go up 1, 2, 3, 4, so we actually add 2 right from -2. It's -1, 0, 1, and 2. So the vertex is right there. The x coordinate, of course, it doesn't change. It's still 1. But the y coordinates now is at 2, right? Likewise, from the center, you go down 1, 2, 3, and 4. So the other vertex, the x doesn't change, but the y coordinates now is at -6, is 4 units below the -2. That's how I locate the vertex 2. Now, when you locate the vertex 2, you again from here, from the center, you want to plot the point where b equals 2. So you go 2 units to the right, you got this point, which is now at 3, and 2 units to the left, and now it will be at -1. Okay, 1, 2, 3, 4. And then you draw an ellipse. Okay, you may want to draw the rectangular box first through these 4 special points again to help you sketch the ellipse by hand. Now to find the foci, we have to see root 12. So that means this center, if we go root 12 units away from each side, that will have to locate the focus. Since this is a -1, so we're going to move up root 12. So that means you add root 12, you got this point. Subtract root 12, you got this point. Okay, so in short, the foci will be right here. The x-axis chain is at 1, and then the y is from -2 plus root 12, and the other foci is still x is 1, but the y is now at -2, subtract root 12. Okay, so that gives you the vertices. Then for the center, for the foci, we have all right, this is the foci. So another foci, center vertex. All right, actually we are done, and it's just a rough sketch of the graph. Now, one thing you should notice is the ellipse in example 2 compared to the ellipse in example 1. Besides the fact that one is horizontal, one is vertical, you see that one is look more like a circle, right? It's not so close to the circle. That one looked pretty long, like elongated. So in order to measure the ovalness of an ellipse, we will form the ratios between the C and A. You notice that here, again, the C is the distance from here to here, and then the A is the distance from here to here. Now, if C is relatively small compared to A, then you have pretty close, more like circle or ellipse. Imagine when C is short. I mean, if C is short, that means your two foci are close to the center. Then your ellipse is actually more circle, right? More like a circle. In the extreme case, when C is 0, right, then you have exactly one focus, and we have a circle. On the other hand, when you see that the foci are far away, so the C is long, or it's close to the distance of A, then we have a elongated ellipse. So in short, if we look at the ratio of C over A, now this ratio is always less than 1, bigger than 0, right? Because C is always smaller than 1, and it's positive. And so this ratio will tell us how or measure the ovalness of the ellipse. And we call this ratio the eccentricity. Okay. Right, to measure the ovalness of the ellipse, we define the eccentricity E to be the ratios of C over A. And because C is smaller than A, bigger than 0, the E, that ratio between 0 and 1. For an ellipse that is nearly circular, E is very close to 0. And for a elongated ellipse, E is close to 1. Because now the C and the A are almost the same length. Now, in general, E will be smaller than 1 strictly But then extreme case is when E is bigger than 1. So if you imagine if E is bigger than 1, that means your C is longer, right? So instead of the two foci, C is the center. But if this one actually moves outside of the ellipse, right? So it's going to be here. Then what happened is the two, instead of, you see the foci is always like inside of it. So think of this as like two part of the ellipse, right? So it's going to be point this side. But if the focus is outside, then this P kind of turn outward. And that one raises it up this direction and open the other way. Then we no longer have the ellipse, and we have two branches of what we call a hyperbola. Okay. So what is hyperbola? The hyperbola is a set of all points for which the absolute values of the difference between the distances from two distinct fixed points called foci is constant. It's constant. Okay, so what this really means, if you look at, okay, let's say this is the hyperbola. If you have, it has two fixed points like before, right? These two fixed points called the foci. You pick any points on the hyperbola to measure the distance from these two foci with D2 and D1. If you take the difference, D2 minus D1, it is fixed, constant. Right, so D2 minus D1, let's say it's equal to 2A, or some constant. It doesn't matter where you are at, right? So if you pick this, measure distance, measure the distance, you take the longer, subtract the shorter, it's gonna have the same number. Okay, so that's what it means. Now the line through the two foci, okay, like before, draw the line through the two foci, intersects the graph of these 2 points. These two are still called vertices. Now the line segment connecting the two vertices here, we connect these two, is called the transverse axis. The transverse axis. Remember, we call the major axis an ellipse, but now we call the transverse axis. The reason we call transverse axis is because there's no minor major here, so that's really it's the axis we call transverse axis. The midpoint between the two vertices is called the center. Of course, that's center, right? And what else we have? Now, in the hyperbola, we have two special lines that are called asymptotes. So, in fact, there is a rectangular box. So you draw the rectangular box here. Then you draw the line through the corners of rectangles. This will serve as an asymptote to the hyperbola. Okay, so the hyperbola has two asymptotes that intersect at the centers of the hyperbola and then through the corners of this rectangular box. Now, what's the equations of the hyperbola? Well, if we define the same as the distance from center to vertex, C is the distance from the focus, where the focus now has length bigger than the C, bigger than A. Then we have the following standard form. The standard form hyperbola center HK and transverse axis of length 2A is these two formula. And look at these two formula. Well, what's the difference? Well, the comparing with the formula 1 to the ellipse, we had the minus sign instead of the plus signs. That's the other difference. In the second formula, instead of we swap the a squared and b squared in the bottom, like an ellipse, we swap the numerator. See the 1 minus k come over here, x minus h come over there. If we have that, then we will have the vertical transverse axis of the hyperbola. Now the foci lies on the transverse axis, as we know, right? But the C now it's calculated using the formulas exactly the same as the Pythagorean theorems. So C squared equals A squared plus B squared rather than A squared minus B squared in ellipse. Okay. Right. I'm going to stop right here and start an example in the next video. I don't want to make this too long.